Class example number 1, we're going to look at the claimed proportion of different colors of M&Ms claimed by the Mars Candy Company. They claim that 13% of M&Ms are brown, 14% are yellow, 13% red, 24% blue, 20% orange, and 16% green. So the question is, based on your bag of M&Ms, answer the following questions. So what I did is I opened up a bag of M&Ms and I first counted how many M&Ms there were. And how many did I find? 55. Then I basically used that total 55 to get the expected number of M&Ms. So for example, to get this cell here, I took 55 times what? 0.13. And I got 7.15. Now obviously I can't expect 7.15 M&Ms to be brown, but we're going to leave that 0.15 in there for precision. Okay? And I did that for yellow, red, blue, orange, and green. You guys get how to do the expecteds? So you're basing the expecteds on how many M&Ms are in your bag. Not all of you are going to have 55. Some of you are going to be really happy and maybe have 57, 58. Some of you are going to be really sad because you only have 52, 51, whatever. All right? Then the next part is you have to find the actual counts. So these are counts because they're counts of each color. So we just count how many brown there were: yellow, red, blue, orange, green. So I had 6 brown in my bag, 9 yellow, 7 red. And you want to double check that all of those add. So if I were to add all of these up, they do total 55. Okay, so that's the first thing you're going to do. That's going to be for part A. Then you're going to take that and complete a chi-squared goodness of fit test to see how well the proportions of colors in your bag fits the M&M's claimed proportions. So step 1 of that is to write the hypotheses. So the null hypothesis is going to be that the distribution of colors is as the company claims. Or you could be specific there and say, 13% brown, et cetera, et cetera. I got kind of lazy and just simplified it to say as the company claims. Remember, the null hypothesis is the normal thing, the proposed model or the theory. The alternative is going to be that that theory is not true. So the distribution of colors does not match the M&M's claim. So to run the test then, so this is our think stage here on this slide. We have to check our assumptions and conditions. So we have to say we have counts, the data are counts of each color. The data in the groups are independent. That seems kind of reasonable. We would assume that a bag of M&Ms has some sort of randomization, right, from the whole vat. There's some sort of manufacturing process that puts M&Ms into the bag randomly. And we have to assume that a bag is less than 10% of all M&Ms. Right? So we have that randomization and 10% again. And that would be pretty sad if one bag was not less than 10% of all the M&Ms, because there would only be 10 bags of M&Ms in the world. And that would be quite sad. I think I forgot to write down the 10% in the notes, didn't I? Yeah, I did. All right, and then the other part is the data sufficiently large? So are all the expected counts greater than or equal to 5? So what I have to do is I have to look back at my data. Here's all my expected counts. Are they all at least 5? Yes, they are. If they weren't, then we technically wouldn't be able to proceed. Or maybe we'd proceed with caution. Okay? So now we go to the show stage. So we have to show our work. And our work to calculate chi-squared is going to be to use this formula. the sum of the observed minus the expected squared over the expected. So what I have is I have calculated that for each cell. So here's my brown cell. There's really just 5 or 6 cells here. So brown, I have my observed 6 minus my expected 7.15 squared over 7.15. So what that basically does is you get negative 1.15. So that means we observed 1.15 less brown M&Ms than we expected. You square that to get rid of the negative, and then you divide that by the 7.15 to create a feel of how big it is relative to the size. Because a difference here from, basically that's like 1.15 more than, or 1.15 less than the expected of 7.15. That's a pretty considerable distance. If it were 1,000,002 and we expected 1,000,001, is that a very considerable difference? No. So it's all relative to how big the expected is. So that's why we're dividing by the expected here. So you can see for that cell right there, the end answer is in green. If you were to calculate that, you'd get 0.1850. So then you do that for each cell. So then you go to the yellow, and you would calculate that. And you get 0.2195. And you do that for the red, and the blue, and the orange, and the green. And the sigma symbol right here means add all of those together. So you take the 0.1850 plus 0.2195 plus 0.0031, etc., and you get 3.8242. That is the chi-squared statistic. So then to find the probability, or the p-value, then we go to our distributions, and we find, I think it's number 8, chi-squared CDF. So we take that and then type in our statistic, 3.8242, comma 99. And the other part we have to put in is the comma degrees of freedom. So there were 6 cells, one for each color or category, right? So there's n minus 1, which is 5 degrees of freedom. 6 categories, so 5 degrees of freedom. And that's how we can get our p-value, 0.5750. Now in terms of showing your mechanics, this is a little more work to show your mechanics. You have to show how that chi-squared formula works. So you need to show a considerable amount of work. You certainly can run a test on here. I would find the chi-squared goodness of fit test, or chi-squared GOF. I don't believe, there's one of the chi-squares that the calculator does not have if it's an 83 plus, the black ones. The blue one should have them all. So what I need to do to run the chi-squared goodness of fit test, however, on the calculators, I need to put the observed data in a list and the expected data in a list. So I'd have to go to stat edit and put this data in. So in list 1, I'll put my observed 6, 9, 7, 16, 6, 11. And in list 2, I'll put my expected. So I have to actually do that work and figure out these expecteds. And then I go and run the test again. So I put my observed in list 1, my expected in list 2, degrees of freedom were 5, and I calculate. And that's, again, you can check your work. You get the chi-squared 3.8242 the p-value, the degrees of freedom. And then this other thing we're going to talk about in just a second, these are basically the component residuals. It's basically what this is showing is each component that would be added together to get that chi-squared. So if you look at the first one here, it's 0.1849. That says 0.1850 right here. And you could see all of these components in there. Okay, so it reports that as well. So then after you've done that, then you have to tell. So since the tell is very similar, since p is high, 0.5750, we will fail to reject the null hypothesis, which means there is no evidence to suggest that M&M's claim is inaccurate. That's all we need to say. Okay? Now what's going to happen is, some of you, as you open your bag, are going to end up rejecting the null hypothesis because of sampling variation. Even though it's probably really true that M&M's is adhering to these proportions, sampling variation will tell us, if we use an alpha level of 0.05, 5% of the time we might observe something that appears pretty rare, right? So 5% of the time we might get a p-value lower than 0.05, even when the null is true. So this is from a previous year here. Student actually opened up their bag and got this, and these are their actual number of brown, yellow, blue, green, orange, red, and below that are the expecteds, and then right here are the chi-squared components. So for example, this 2.3 would be 3 minus 7.02 squared over 7.02. So the question is, show the results of someone in class who rejected the null hypothesis and analyze the components to say more about how the distribution is wrong. So where was their bag of M&Ms bad in fitting to the model? What colors? What?
Red.
Red? And you can see that because look at red, it has a very high component score, right? 7.02. Didn't brown as well? Right? See how the actuals are very far from the expected? That's going to leave us a larger component score at the end. I'm sorry, this isn't the component score, this is. So probably the largest errors are red and green, right? And we can see there are too many. Those numbers actually were a lot higher than what was expected. So this bag of M&Ms had too many red and green, and on the flip side of that, it had too few. I look at the next two highest components, these two, it had too few brown and orange, right? That's where it went wrong. It wasn't too bad in fitting to the blue, was it? The component score was almost 0 because, look, there were almost exactly the number we'd expect in that bag of that color. Make sense? So what you're going to do is you're going to open up your bag, count how many there are, count how many there are of each color, record your data in a table like I did here, and then you're going to finish that problem. I know I showed it all to you, but you're going to do it for your data. Your answer for the null and alternative will be the same in checking the conditions, but just redo that, and then we'll kind of see how all those end up. All right?